This is Sriraj, and now as a part of our science project, I am going to explain the following four topics: Hermite's polynomials, Lagori polynomials, moment of inertia matrix, and rocket dynamics using Hamiltonian and Lagrangian mechanics. Now I am going to explain about Hermite's polynomials. Actually, in mathematics, Hermite's polynomials are a classical orthogonal polynomial sequence. Hermite's were first defined by Laplace, though in a scarcely recognizable form, but studied in detail by Chebyshev. But his work was overlooked, and the polynomials were named after Charles Hermite. Now, Hermite's differential equation is y double dash minus 2xy dash plus 2ny equal to 0. If n equal to 0, 1, 2, 3, so on, the solution of the Hermite's equation is given by Hermite's polynomial Hn of x. The polynomial also given by Rodrigues formula, where Hn of x is equal to minus 1 whole power n into e power x square into dx power n by dn power into e power minus x square. Now substituting n equal to 0, 1, 2, 3, we'll get few Hermite polynomials where h0 of x is equal to 1, h1 of x is equal to 2x, and h2 of x is equal to 4x square minus 2. Now we can derive a recurrence relation for the Hermite's polynomial, where hn plus 1 of x is equal to 2x into hn of x minus 2n into hn minus 1 of x. Now properties of Hermite's polynomial. Hermite's polynomial is a polynomial of degree n. Its leading coefficient is has 2 power n. Now we will see orthogonality in these Hermite's polynomials. Now consider hn of x a n degree polynomial, and the polynomial is orthogonal with respect to weight function, where w of x is equal to e power minus x square. Since it is orthogonal, it should satisfy the following condition: integral of minus infinity to infinity e power minus x square into hm of x into hn of x is equal to Dirac delta of m comma n into 2 power n into n factorial into root pi, where delta of m comma n is Dirac delta, which is equal to 1 if m equal to n and equal to 0 if m not equal to n. Now we can have a orthogonal series using Hermite's polynomial, where f of x is equal to a naught h naught x plus a1 h1 x plus so on, where ak is given by 1 by 2 power k into k factorial into root pi into minus infinity infinity e power minus x square into f of x hk of x dx. Now Hermite's polynomial has many applications. It is used in probabilities such as Edgeworth series. It is used in numerical analysis as Gaussian quadrate, and in physics to get eigenvalues of quantum harmonic oscillator. Now I am going to explain Lagori polynomials. In mathematics, Lagori polynomials are named after Edmund Lagori. These Lagori polynomials are solutions of Lagori's equation, where the equation is of the form xy double dash plus 1 minus x into y dash plus ny equal to 0. It is a second order linear differential equation. This equation has a non-singular solution if and only if it has a non-singular solution if and only if n is a non-negative integer, that is n greater than or equal to 0. Now for this Lagori polynomial, there is a representation given by Rodius. This representation is ln of x is equal to e power x by n factorial into d by dx d power n by dx power n into x power n into e power minus x. Now substituting n equal to 0, 1, 2, 3, we will get a few Lagori polynomials, where L0 of x is equal to 1, L1 of x is equal to minus x plus 1, L2 of x is equal to x square minus 4x plus 2 by 2. We can get a recurrence relation for the Lagrange polynomials. The recurrence relation is Lk plus 1 of x is equal to 2k plus 1 minus x into Lk of x minus k into Lk minus 1 of x by k plus 1. The closed form for Lagrange polynomials is Ln of x is equal to sigma k equal to 0 to n nck into minus 1 whole power k by k factorial into x power k. The Lagrange polynomials also follow orthogonality. We will study the orthogonality of Lagrange polynomials. The Lagrange polynomials are orthogonal over 0, infinity with respect to weighing function w of x is equal to e power minus x. So we have integral 0 to infinity Lagrange n of x into Lm of x into e power minus x dx is equal to delta m comma n, where delta m comma n is Dirac delta function, where it is equal to 1 if m equal to n, 0 if m not equal to n. Now we will see some applications of Lagrange polynomials. Lagrange polynomials are used for Gaussian quadrature to numerically calculate integrals which are of the form integral 0 to infinity f of x into e power minus x dx. It is also used in quantum mechanics to calculate the radial part of solution of Schrödinger wave equation for one electron atom such as hydrogen atom. Now I am going to explain about moment of inertia matrix. First we need to know what is moment of inertia matrix. Actually it is a matrix consisting of all scalar moments of inertia when a rigid body is treated as system of particles. Now I am going to explain about parallax theorem. In this we need to calculate the moment of inertia about a fixed point whose position vector is given by r bar, and we know that a center of mass of the body whose position vector is given by c. Then moment of inertia of the body about that fixed point will be equal to IR is equal to minus sigma I equal to 1 to mi into Ri minus r whole square, where r is the position vector of ith particle and mi is the mass of ith particle. Solving this will get moment of inertia of the form IR equal to IC minus m into d square. Now we will calculate the moment of inertia about any arbitrary axis. Moment of inertia about an arbitrary axis. Let IL be the moment of inertia about arbitrary axis passing through a point whose position vector is r, and we know that vector along its direction is c. Then IL will be equal to s into minus sigma I equal to 1 to n mi into delta Ra whole square into s, where delta Ra is equal to Ra minus r, and r is the position vector along the random axis point. This will be equal to s into IR into s, which will be equal to s transpose into IR into s. Now consider a arbitrary particle AI. We want to calculate delta Ra perpendicular, where delta Ra perpendicular is a vector perpendicular to the change, that is delta Ra, and hence delta Ra perpendicular is equal to Ra minus r minus s into Ra minus r into s, which will be equal to difference of moment of inertia matrix minus s into s transpose into delta Ra. Now we need to calculate mod delta Ra whole square, that is the magnitude of the vector whole square, which will be equal to minus s into delta Ra into s. Now IL is equal to s into minus sigma equal to 1 to n mi into delta Ra whole square into s, which can be rewritten as s into IR into S is equal to S transpose into IR into Hence we have derived the equation for IL. Now we need to know the application of this moment of inertia matrix. It has many applications. It is used in calculation of angular momentum, angular velocity, and kinetic energy of particle about any axis. Also, we can analyze the mechanics of spinning top using this moment of inertia matrix. Now I am going to explain rocket dynamics using Lagrangian mechanics and Hamiltonian mechanics. Now I am going to explain rocket propulsion using Lagrange's mechanics. Now consider a rocket. Let's its generalized coordinates be q and generalized velocity is p q dot, and so it is at a distance q from the earth. Now its kinetic energy will be half mv square, which will be equal to half m q dot square. Its potential energy will be equal to mg into height from the earth into q dot. Now we know that Lagrangian for a system is equal to difference of kinetic energy and potential energy. Hence L is equal to kinetic energy minus potential energy equal to half m q dot square minus mg into q dot. We know that Lagrangian equation is dou L by dou q minus d dt of dou L by dou q dot equal to 0. Now for the system, we calculate the dou L by dou q, which is equal to minus mg, and dou L by dou q dot is equal to mq dot. Now substituting this in the above equation, we get minus mg minus d by dt of mq dot equal to 0, which will be equal to minus mg minus m into d by dt of q dot minus dm by dt into q dot equal to 0. We'll get minus mg minus mq double dot minus dm by dt into q dot equal to 0, where dm by dt is the change of mass with respect to time as the rocket mass changes. Now its equation of motion will be mq double dot plus dm by dt into q dot equal to minus mg. Hence it is the equation of the rocket dynamics using Lagrangian equation. Now I am going to explain rocket propulsion using Hamiltonian mechanics. We have calculated the kinetic energy and potential energy above, which is kinetic energy is equal to half m q dot square and potential energy equal to mg into q dot. Now we know that for Hamiltonian mechanics, H is equal to sum of kinetic energy and potential energy. H is equal to kinetic energy plus potential energy is equal to half m q dot square plus mg into q dot, mg into q. Now Hamiltonian, we know that Hamiltonian equation is dp by dt equal to minus dou h by dou q, and we will get p from the Lagrangian mechanics, where p equal to dou L by dou q dot equal to mq dot. Now substituting p in the above equation, we get d by dt of mq dot equal to minus dou h by dou q. From the above equation, dou h by dou q equal to minus mg. So substituting it, we will get d by dt of mq dot equal to minus mg. Derivating it, we will get m into q double dot plus dm by dt into q dot is equal to minus mg. This is the equation of motion for rocket propulsion using Hamiltonian mechanics, where dm by dt is the rate of change of mass with respect to time. Thank you for watching.